Hello everyone. Today we'll be discussing how the use of a modified form of Bernoulli's equation can help us analyze losses in a fluid system. You can see here that we're starting with the standard writing of Bernoulli's equation for reference. Each term is in units of pressure, but are often referred to as energies. For example, we have pressure energy, kinetic energy, and gravitational potential energy. Ideally, the total energy in the system is constant, meaning that we have the same terms on both sides with no losses included. To be clear, the energy they're referred to is energy per unit volume. Now we'll modify the equation so that we can analyze losses in a system. To do this, we will divide everything by rho g, like so. That will leave us with an equation that looks like this. Now each term is expressed in length instead of pressure, and instead of referring to them in terms of energy, we refer to them as heads. It is convenient for our calculations and conceptualization to work in this form. We have pressure head, velocity head, and elevation head on both sides. These represent the depth of the column of fluid. Ideally, the sum of all these is a constant, just like what we had in the original version of Bernoulli's equation, meaning that the total head would be constant for the system. Now we will be adding a new term to the right side, which is this term here. This is called head loss, denoted as H sub L. This head loss term contains all of the losses in the system and is also expressed in meters. Here we have a diagram that illustrates why we like to work in terms of head rather than pressure. On the left side we have a tank that has no energy due to pressure or velocity, only its elevation. This elevation provides the baseline energy for the entire system, so we mark that elevation as the energy line, which is ideally constant throughout the entire system. If we were to have losses in this system, the energy line would gradually decrease as we go downstream, meaning that the elevation the fluid could reach decreases. The other line in the diagram is the hydraulic grade line. This represents the total head of the system minus the velocity head. So as the velocity of the fluid increases, the hydraulic grade line decreases. Head loss can be broken down into two components, called major and minor head loss. Major head loss is the sum of frictional forces over the length of a pipe. Minor head loss is the sum of losses due to things such as bends, valves, and changes in the shape of a pipe. We will now learn how to calculate these losses, starting with the major losses. Here we have the equation for major head loss. It includes the ratio of the length of the pipe to its diameter, the velocity squared, and 2g. We also have this F term right here. This is the friction coefficient that we will have to find separately. To do this, we are going to have to look at a Moody chart, which can tell us the loss coefficient based on a few different factors. Here we have a Moody chart, which looks complicated, but using it really isn't that difficult. On the bottom of the chart we have the Reynolds number. On the right side of the chart we have the ratio of the roughness coefficient of the pipe material to the diameter of our pipe. That ratio is called the relative roughness. And on the left side we have the friction coefficient that we need to calculate major head loss. To use our Moody chart, let's quickly review how to calculate the Reynolds number of a flow. The Reynolds number is equal to the density of the fluid times the velocity of the flow times the diameter of your pipe divided by the viscosity of the fluid. And below 2100 we call this laminar flow, and then above 4000 we call this turbulent flow, and anything in between we consider transitional, which is somewhere in between laminar and turbulent. Now I'll show you how to use the chart. Once you have the relative roughness and the Reynolds number, find where the vertical line corresponding to your Reynolds number and the curve corresponding to your relative roughness intersect. The horizontal line where they meet will give you the friction coefficient on the left side of the chart. Now with the dimensions of the pipe and the velocity of the flow, you can calculate major head loss. So let's find a friction coefficient real quick. Let's say our Reynolds number is 10 to the 5, and our Relative roughness is, say, 0.002. So we'll follow this curve from 0.002 out until we're above 10 to the 5. So that's about right here. And then we'll follow the horizontal line over until we meet our friction coefficient on the left-hand side, which is, in this case, 0.025. Once you have that, you can plug that back into your major head loss equation. Now we will learn how to calculate the minor losses of a system. Fortunately, this process is quite a bit simpler than calculating major losses. The equation of minor head loss as shown here is KL times V squared over 2G. On our chart, we have a list of various fittings and bends, along with their corresponding coefficients. Simply pull the ones you need from the table, add them up, and plug them into the equation. The only exception is for a sudden change in the area of the pipe, in which case we have these little charts to help us. We'll need the ratio of the areas according to the situation, then we get a corresponding KL from the curve shown here. If there is a problem where we need to consider both major and minor head losses for a system, we simply need to calculate the head losses separately and take the sum of both of them to get the total head loss, which is HL in a modified Bernoulli's equation. Alright, lastly we're going to find the total head loss in this 2 cm diameter galvanized iron pipe. The volumetric flow rate is given as 0.04 meters cubed per minute, and the viscosity is given up here as 0.0011 Newton second over meters squared. Okay. So our diameter is given here, 2 centimeters, or 0.02 meters. Pipe material is given as galvanized iron. These turns are said to be regular 90 degrees threaded, and this valve here is a wide open globe valve. So we'll need all that to find our friction coefficients. Okay, first thing we're going to do is we're going to get this Q and we're going to convert it into meters cubed per second. That'll help us convert into velocity later. So we have 0.04 meters cubed per minute. We want that in meters cubed per second. So we do 0.04 over 60 gives us 6.67 times 10 to the negative 4 meters cubed per second. Okay, next we're going to go to our table very quickly and grab our relative roughness or equivalent roughness for galvanized iron, which is 0.015, and we're going to end up calculating the Reynolds number and going to this table and getting our friction coefficient. So let's do that. So the velocity is going to be Q over A. This Q is our 6.67 times 10 to the negative 4. Our area is 0.01 meters squared times pi, 3.142 meters squared. Okay. And the velocity comes out to be 2.122 meters per second. So here's our equivalent roughness. This is going to be our relative roughness. And the Reynolds number is that 1,000 times velocity, 2.122, times diameter of the pipe, 0.02 meters, over the viscosity of the fluid, which was that 0.011. Okay, so now with all this information, this relative roughness and the Reynolds number, we're going to go back to our chart and we're going to calculate that. So we're going to find the curve for the 0.0075. We'll call that about 0.008. Follow that until we're over our Reynolds number, which is 38,000. And we go over and get about 0.037 as our friction coefficient. Okay, and we're also going to grab our coefficients for the turns in the pipe, which are these regular 90 degree threaded. We have 1.5 for both of them, and then the globe fully open is going to be a whole 10. So now we have our friction coefficient, which is 0.037. So And the total length of our pipe was 8.5 meters. So the major head loss here is going to be this friction coefficient times the 8.5 meters over the diameter of the pipe times this velocity squared over 2 times 9.81, and we got 3.61 meters. And then we're going to calculate the minor head loss, which is 2.98 meters based off of this equation here, where we put in this 1.5 plus 1.5 plus 10. This is our KL. And then we have V squared, again, 2.122 meters per second over 2G. And that gives us 6.59 meters as our total head loss.